Hello and welcome to another video, and in this one we're gonna take a look at how to move our object like this. So we're gonna pick up from where we left off last time like this, and our end goal is to reach and render something like this. So let's get started. Alright, first thing to begin with, we're gonna go ahead and remove this code right here because we're gonna do it later on um, in a render function. So I'm gonna go ahead and remove that. And next thing is I'm going to first we're gonna change this so we can use up the whole canvas. So in order to do that, what we're gonna do is adjust these values real quick. Right here, this one, it's used to push the object away from the camera along the z-axis. Instead of being -1, I'm gonna make it 5. And need to do one more thing here. Let's go back here. And then projection matrix. Right now we do no scaling on the x-axis and no scaling on the y-axis. I'm going to add a perspective projection setup, and that is 1 second. All right. So yeah, we're going to add this line right here, and for the 10th index, we're going to put 1. So this we're going to make it 0. Sorry, not 1. We're going to make it 0, and this is the perspective projection setup. Next, we're going to add another line here, and then this one we're going to the 15th index. And we're going to use the entire canvas for projection like this one and change this one from -1 to 1. And hopefully when you go back, there we go. So we don't have our canvas, but you can see we have shrunk it down now. So that's first step in the process. So going well. Next, what we're gonna do is um, in order to make it move, we're gonna set an interval and call the render function every 10 milliseconds. So to do that, we're gonna right here set interval. We're gonna use that function, and then we're gonna make our own render function, and then we're gonna set it to 10 milliseconds. Um, 1 second. If we go here, all right, all is fine. One thing that I would like to show real quick that Dr. Riggs did before we jump into that render function is when we go to our load shader function. After we have our line for compiling the shader, this is just a quick way to check if the shader compiles successfully and get the compilation log. So what we're gonna do is we're gonna do let compiled equal gl dot get shader parameter and gl dot compile status. So we're gonna get the compile status, and that way this just helps us debug um, when we run into issues. Then we need to get the compilation log by doing let compilation log equals gl dot get shader info log, the capital L log, and in here we pass in the shader. In the previous one we passed in the shader and we get the compile status. So next line we're gonna go ahead and do console.log, and this way we can, when we go into inspect, we can see. So we're gonna pass in the compiled and compilation log. Um, compilation. Why is this erroring? Ah, I forgot a comma. All right, there you go. Silly mistakes. All right. Now that should hopefully work. I might have messed up something. Let's see. Get shader info. I think I mistyped it. Let's go back here. It's not a capital G. It's a normal G. And yes. All right. So you can see these true. That's from line 74. Um, that is line 74 right here. So it's just saying true and true, so which means we're good. our status is good and we're compiling correctly. So that's a quick debug thing for us that can be useful. All right, now let's get back to our render function. So we're gonna do function render. There we go. Um, so what we're trying to do is animate our object, right? So in order to do that, first we're gonna do let temp equal 0. So we're gonna initialize the variable for the animation, and then we're gonna do temp plus equal 0.01, and this will use it to increment the animation variable, and then the render function will be called repeatedly to draw the scene. So now in here we're gonna do our clear color, to get that black canvas. So we're gonna do gl.clearColor 0, comma 0, comma 0, comma 1. Get our black, and then we need to do gl.clear, and then go ahead gl.color underscore buffer underscore bit, or gl.depth underscore buffer underscore bit. Okay, let's go check it out. We have that. Cool. Next thing we're gonna do is move this from here. Second. Alright. Move that from there to here. And there we go. Now, we're making progress, right? We got our canvas back. We have our object looking good. And so before we go any further, we're gonna make a quick change to how we had it set up. And this is something that Dr. X showed, is to rename these our position, projection matrix, and model view matrix, as it'll make more sense to have it renamed to a projection, a U projection matrix, and U model view matrix, and name them in a camel case format. So let's go ahead and do that real quick. A position, and then U projection matrix, U model view matrix. All right, but we're not quite done yet because we need to go to our vertex shader and do the same, or else it's not gonna work. A position, U projection matrix, U model, and a position. All right. So with that, I believe does that. So it should be renamed, and yes, okay, we have no errors. Um, see, we get that two trues. So that's good. Now that that's fixed, what we're gonna do is we're gonna move this line right here that gets the uniform model matrix, and we're gonna move it to in our render function. So this way we pass a model view matrix and the time to the shader, and we upload the model view matrix each time when we repeatedly call the render function. So we're gonna go right below here and do that. Now, in order to animate the object along the y-axis, one second before we do that. Okay, still works. Just gotta make sure, in order to animate it, what we're gonna do is we're gonna do model view matrix 13th index and go 2 times math. Because if we do temp, hold up, if we do temp, let's see what happens. Yeah, so the thing with temp is when we do just temp, it just goes off our screen. We don't want that. What we want to do is we want to have it move back and forth and stay in our canvas. In order to do that, we're gonna do math.sign. Let's see what that does for us. So now we have it go, It's moving. Let's do times 2 times that. All right. 1 second. All right. There we go. 2 times that. Now it's, moving a lot quicker and it's looking good. So making some good progress. We're having our thing move. Um, the next big thing to that we should focus on is currently, we just have it do one color. Um, what if we instead have it, render based on the normals? So in order to do that, we're gonna go ahead and create a normals list for our vertices. So let's go ahead and do that. And generally we just go 0, 0, 1. There we go. Now we just need to copy this, put it, we have 8. So we have that. All right, there we go. So now we have our normal setup for 8 vertices, and this will be used for like the light calculation. So now instead of just being one green, we'll have it based on the normals. Um, and in order to actually get it in here, just like how we did the vertex positions, we need to make another set of this 5 lines of code right here. You see this? So we need to replicate this, just copy paste it, but then now it'll just be for normals. So one key thing to do right here is change this to just vertex position. All right, perfect. So now we'll just go ahead and copy this, paste it right there. Now we're just gonna change this to vertex normal. So change this to vertex normal, and then we need to rename this, and rename this as well. But this is something we're gonna have to do in our vertex and fragment shader, which we'll add in a second. Instead of passing in the positions, we'll be passing in our normals. What did we just name it? Normals? Yep. All right, now we pass in our normals there. So that's perfect. So now we bind the normals to the shader. We do that using these 2 lines of code right here. We create a new buffer for the normals in this line, and then we upload the normals to our buffer. And then in this one, we get the location of the a normal attribute in the shader. And in this line, we define how to read the normal data, the 3 floats per vertex. And then in this line, we enable the a normal attribute. So now that that's set up, let's go ahead and go to our vertex shader. That's usually where we would like to begin when we're editing this. So we have our model view matrix, the projection matrix. We have attribute vector 3a position. Now we're gonna go ahead and do a attribute vector 3a normal, like I said, that we will be using there. And what this does is it's the vertex normal in model space, and this attribute will represent the normal vector of the vertex in model space, and it'll be used for lighting calculations. Um, so what we're gonna do is we're gonna go here. We have all of this updated. We're gonna make a 1 second. Yep. All right. So just like how we have a position, that is a position. So that's the vertex position in model space. We're gonna make a varying version of that pass the vertex position for the vertex shader to the fragment shader, and this will be interpolated across the surface of the triangle. So what we're gonna do is attribute vector vector 3 v position. Then we're gonna do the same attribute vector 3 v normal. Perfect. Then we're gonna have to pass it here so that way we can get it in the fragment shader. So we're gonna do v position equals a position, and then v normal equals a normal. Right. Perfect. Now let's go to the fragment shader. And then in here, all we need to do is get our varying vector 3 v position. And this was what was passed from the vertex shader, and it contains the position of the vertex in model space. And same thing goes for varying vector 3, but then this will use it for light calculations. I cannot type. All right, there we go. V normal. All right, now in here, I believe we can just do V normal, normal, and what is this error? One second, I'm gonna check what the error is about. I think it's because we might be X. No, one second. E normal, inspect. Alright, I was just getting ahead of myself. We'll go ahead and set up the UV as well before you know, for it to work properly. So let's add the UV list. Let UVs equal, oops, right. And so this will where we define the UV coordinates for each vertex and to be used for texture mapping. And we're just gonna go ahead and do it for vertex 1 through 8. We go 0, comma 0, and 1, 0, 1, 1, 0, 1. And all we need to do is just copy paste this for the next 4 vertices up to 8. And then, just like how we did for A normal, that setup, these 5 lines, we just need to copy that and paste it here. And then we'll change it to vertex UV. Vertex UV. There you go. Then we need to change this to A normal to A UV, which we will have to add in our vertex and fragment shaders. And then instead of passing in normals, we'll pass in the UVs. Perfect. Um, that's looking good. Now we will go ahead and yeah, let's go back here. That's still gonna be error. All right, we're gonna go to our vertex shader first, as I've said, and just like how we did A position, A normal, V position, V normal, we're gonna do AUV and VUV. So have the attribute. Okay, I think I might know where one of the things I messed up. Okay, so this one is a vector 2. UVs are vector 2. So keep that in mind. This one is varying. That's one of the issues. Okay. Alright. do that for varying vector 2 VUV. All right. So this will obviously pass it, the vertex shader to the fragment shader. One more thing is the actual part where we do pass it is VUV equals AUV. All right. Now our vertex shader is mostly set up, and we will move to our fragment shader. Um, so yeah, let's do that. Normal. Now we just need to do a varying vector 2 of VUV. So now we can use this for texture mapping. So we should just be able to, I was getting ahead of myself there. VUV dot X, VUV dot Y, and then this should just be 0 or something. 1 second. Right. So as you can see, I was able to figure out the bug I had. Um, One was missing a semicolon here is pretty important. Um, so that, and then I set VUV dot X. We get the VUV dot X and VUV dot Y, and so we just uh get the for the we calculate it using the UV coordinates, and we get it for the red channel and the green channel. And that creates like the dynamic effect of where the color is changed based on the UV coordinates. Um, so that's pretty cool. And then one more thing is in here I said 8. That's my fault. It's 7. We only have 7 here. In my notes I had 8, so I put, so you want to delete the last row here, -7, as you can see, for the normals and UVs. And then the last thing here is change, like I said, UV is vector 2, so it's a vector 2. When we copied and pasted, it was vector 3 from the normals. So make sure to change this to 2. And yeah, those are the changes I had to do. And now, our object looks like this, which is pretty cool. The next thing to do is calculate the lighting. So we can define a light position and as a normalized vector. And to do that, we're gonna go to our vertex. No, vertex shader. We're pretty much done with mostly. So we're gonna go to our fragment shader. I'm gonna make this vector 3 called the light position, and so the light position is animated using this sign of the time variable v. We're gonna include v time later on, which will kind of make it dynamic. But for right now, we want to have the light move along the x-axis, and we'll use a normalized function to ensure the light direction is a unit vector. But yes. So yeah, let's go ahead and do normalize, and then a vector 3 0, 1, and then what we're gonna do is we're gonna calculate the dot product between the light direction and the vertex normal. So we're gonna do float d equals dot light position normal. So the dot product will measure the alignment between the light direction and the surface normal. The higher the value means the surface is facing the light, and while lower means it's angled away. And then in order to avoid negative values and not use an if statement, Dr. Rick said it's best to avoid if statements in our WebGL code. So we're gonna do d equals, we're just gonna use the max function. Keep it simple. We're gonna do 0 dot float. comma D. And then in here, we can do times D. One second. So we're gonna take this UV and then do times D, and then add DS here as well. That breaks it, and I think that's because we still haven't defined uh, our our V time. So let's go to our vertex shader, and we're gonna make a uniform float called U time, and this will be the time passed since the start of the program, and this will be what will be used for the animations and like a dynamic effect. And then like we did with the U, we need to make a V time, which will be varying vector, not vector, sorry, float V time. All right. So this will and like we did before, we need to pass it to our fragment shader. So we're gonna go ahead and do V time equals U, if I can spell it correctly, V time equals U time. So yeah. All right. So now we're done with our vertex shader. So I'm gonna move it aside here and then quickly um, kind of talk a few things, which is uniform. The variables are constants for the duration of the draw call, and the attribute variables are per vertex data passed from the CPU to the vertex shader. So A position is the position of the vertex in model space. A normal is the normal vector of the vertex in model space used for lighting calculations. And then AUV is the coordinates of the vertex used for texture mapping. And then the varying variables are passed from the vertex shader to the fragment shader. That's what we're passing over here. Um, and so they're interpolated across the surface of the triangle, providing smooth transitions between vertex values. And the next one, I think that's about it. Transform. All right. So yeah, that's it for the vertex shader. I hope makes sense why we're passing these. Um, so then we'll move on to our fragment shader. In here, we want to do our varying float v time. So we can get it from um, our vertex shader. So, but then in this first one, we're gonna do sine v time and normalize vector 3 not sing sine function. So now the light position is animated using the sine of the time variable v time. Um, and then the the normalized function ensures the light direction is in unit vector. And then obviously we get the dot product and whatnot. And then in this fragment color, um, so the final color of the fragment is calculated using the UV coordinates and the lighting factor D. The red channel is proportional to VUV dot X times D. The green channel is proportional to VUV dot Y times D. And then the blue channel is proportional to D. And this is what will help us create the effect where the color changes based on the U coordinates and the lighting, and hopefully that. No, we're gonna deal with the issues. All right, where is this? Uh, it was a small fix, so it was in the fragment shader code where when we do the calculate the dot product between the light direction and the normal, I just put normal. It's V normal. Like we get the vertex right. This is what we want. Normal is nothing. So yeah, that helps fix it. And now you can see we have like that lighting based like texture. And we went from having just plain green to then calculating based on the UVs to now based on light. Um, in order to So right now, I know I said it'll dynamically based on the light direction as it moves. So we need to make the light, um, you know, like dynamically move. And for that, what we're gonna do is we're gonna use a time variable in our render function. And so right now, if you see, it moves up and down, and then it's the same. The light is the same. But then we wanted the light to dynamically change based on where it moves. And for that, we're going to use GL dot uniform 1F, not L. Keep that in mind. And then we'll do GL dot get uniform location, and then pass in our shader, and then U time. Pass in the U time, and then temp. So this will upload the time variable, and hopefully now you can see it kind of lighten. See, like um, when it gets here, it's nice and bright, and then when it goes down here, it gets darker, and then it gets bright, and then it gets darker. So that's perfect. And then a couple more things I'm gonna do here is I'm gonna do gl dot clear depth. Oh, and this will set the clear depth to 1, and then we're gonna work on this next. So I'm gonna just put it in now itself, which is gl dot enable, which is gl dot depth test, depth underscore test. Um, it's good. And then finally, we'll set the depth function to less than or equal. So we'll go gl dot depth func. This will make more sense once I show, you know how initially our goal is to have like 2 of these objects. So this is what helps with the depth of that. So yeah, that should be everything in terms of new code that we added in order to get this, dynamical lighting and texture mapping that we have done. Now all I'm gonna do is, well, we're into another error. Okay, let's see. GL.depth is not a function. I might have had a typo. Let's see. GL dot clear depth. It's depth func. All right. All right. Okay. See, that fixes it. Okay, we're good. So now we have that right here. The one behind. We have that rendered, as you can see, right? So now we're gonna try to render one in front, and that's gonna be, we're just gonna do that just by copying this, our positions, put a comma here, and then having that duplicated, and what we're gonna do is we're gonna mess with these so we can push it like, you know, farther back. So yeah, so mess with our Z values here. Perfect. And then we're gonna have to do the same for the normals. Uh, Copy paste this, but then instead of it being ones, we're gonna have it twos. Do this real quick. Is that 7? 1, 5, 6, one more. Alright, perfect. So our normals are ready. Now we just need to do the same for UVs. UVs, we don't have to change it. That's done. So now we just need to add these indices. So we're gonna go, we went from 0, 1, 2, 0, 3, 4, 0, 5, 6. So it should be 7, 8, comma 9, and 7, 10, 11, and then 7, 12, 13. Okay, perfect. Let's just, instead of trying them all at a time, let's do 12, render another one. Okay, there you go. So now we'll do 15. We got both of that. We just gotta get the lower one. And we just gotta do 18. Alright. Oh, pressing the wrong one. Okay. There we go. We got our end result. We have achieved, I think, pretty close to that. So yeah, let's see. Yeah. So that's pretty sure that's everything for this video. One quick thing I would like to go over quickly is the fragment shader. I know this one we kind of just added a few things and I did not go into in detail. So the final color of the fragment is calculated using the UV coordinates and the light factor. And then the red and green channels are modulated by the UV coordinates, while the blue channel is proportional to the lighting factor. And this is what creates that dynamic shading effect that combines texture mapping and lighting. This line right here, it ensures that the negative lighting values are clamped to 0, avoiding unrealistic shading, where surface facing away from the light would disappear lit, would appear lit, and then this one, the dot product between the light direction and the surface null determines how much light hits the surface. A value of 1 means the surface is fully lit, while the value of 0 means the surface is perpendicular to the light direction. And then this line, the light position is animated using the sine v time, which makes the light move back and forth along the x-axis over time. And the normalized function ensures the light direction is in unit vector, which is necessary for proper lighting calculations. And finally, to kind of sum it up, um, this is what we have added. We went from just the GL frag color where we're going one color to now, dynamic. And then the vertex shader, we just pass in these our normals and UVs and the time. And then in here we added our interval for our render function so it can draw it every 10 seconds, 10 milliseconds. And then we added a couple like, debug for us to know, make sure that it's compiling, shader's compiling properly. And then we reconfigured our code over here, which, sets up the buffer to now have it do for the normals and the UVs just like it does it for the positions. And then this was just a lot of duplicating, positions and then the normals and UVs, just so we can get, more cool effects. And then we adjusted our model view matrix and projection matrix to use the entire canvas and have our object pushed away from the camera along the Z axis. So yeah, that's it for this video. I hope this kind of was a good where it built off of a previous one. We're able to add more features, and the code. I hope the code made sense. What the new functions that we added. So yeah, that's it for this video. Thank you.